Hello, this is Mrs. Grizafi, and we're on 11.05 for geometry today, and wrapping up this unit 11 on volume and a little bit of surface area mixed into. So this will be the last full lesson in unit 11, and then we're going to have a little bit of review for next class, and then the class after that, you guys will be taking a quiz on unit 11. So that is what we have coming up. So today we're going to talk about a truncated cone. So a truncated cone is created by taking a cone and slicing off the top part of the cone. So the part that includes that vertex right there. So you're taking off like a little cone from the big cone. And another name for this is a frustrum, called a frustrum. So you could see that as well. Frustrum. So again, what we're doing is we're taking this large cone right here. I'm going to do in purple. And we're taking off that dotted line section. So we're removing the dotted line, which would leave us with this right here. So that's the frustrum, or the truncated cone in orange. We're taking this part off, the dotted part. So it asks for number one, what strategy might make sense to find the volume of the cup, the truncated cone? So if I want to find the volume of just the orange, how could I do that? So think about this, maybe pause it, think to yourself, how could I figure this out? How could I find just the volume of that orange cup? All right, so hopefully you're thinking, well, if I take the volume of that whole cone, the purple cone, and then I want to subtract this little cone, this green area right here, minus the volume of the bottom cone. That, which is the dotted on your papers, mine's kind of covered up. That will give us the volume of what's left over, which would be the orange part, that frustrum, that truncated cone. So we'd find the volume of the entire big cone, because we can do that. Then we know how to find the volume of another cone, and then we subtract the green cone, take it away from the purple cone, and we're left with the orange cup. What information would we need to carry this out? Well, we would need to know our formula for a cone. So I just posted the bottom part of your reference sheet, the Regents reference sheet right here. And you can see that you are given the volume of a cone. So I would need to know the volume of a cone, pi r squared h. And in order to find the volume of the cone, I need both the radius and the height of each cone. I need to know what the radius and the height is of the whole cone, the big one, and of the smaller one. And if I know all of those things, I can again find the volume of the entire cone, subtract the volume of the bottom cone, and be left with that cup, or that frustrum. Let's look at an example. And it gets a little bit harder, and we're going to walk through why that is in the next one here. So from here now, it says you're given a cup with a height of 18 centimeters that has a large radius of 5.4 centimeters and a small radius of 3 centimeters. So the cup, that's your frustrum, or your truncated cone. So we know that from here to here, and this is, so right here, this big triangle, and this is a right cone, so it makes a right angle right here, which means it still is right here. This triangle has been drawn outside right here. And the dotted line is that cone that the top cone that we're going to remove, leaving us with just the cup. So this cup part up here is, so again, we're talking about the cup, which is this top part right here. This is your frustrum. We know the height of that is 18 of the cup. So the cup's 18 centimeters tall. The large radius, so where the big hole is at the top, the big circle, that's 5.4 centimeters. And the small radius, so at the bottom of the cup, is 3 centimeters. We're going to want to eventually, we're going to be asked how much this cup can hold. So we're going to be talking about volume. In order to find it, like we said in the first one, which this is number 2, I think. Oh, no, I called that number 2. Scratch that. That's still number 3. So this one, we want to know what is true about the two triangles, meaning this triangle right here, this small triangle, and this larger triangle right here in red. What's true about them? Well, we know they both each have a right angle. And we also know that they both share this top angle right here. So by reflexive, it's congruent to itself. Well, if I know that they each have a right angle, that's one angle in each, and then they share an angle, then I know that these two triangles are similar because of angle-angle similarity. Angle-angle similarity. So again, because they each have a right angle, each have one right angle, since it's a right cone, and they share an angle as well. So if we know that those two triangles are similar, therefore we know that their corresponding sides must be proportional. And that's going to really help us to find some missing pieces that we may need for these types of problems. So B says, set up and solve an equation that could be used to find the value of x, the height of the smaller cone. So they've labeled that for us right here. We're looking for x, which is the height of the smaller triangle or the smaller cone. And we know now that these two triangles are similar to each other. So when we're talking about the triangles, we have to look at the whole side. So we know the little side in the small triangle is x. That corresponds to this big side over here. The length of that would be x plus 18. Now let's match up some corresponding sides since we know they're similar to each other. So I know that I've got the side with the 3 right here, the short side. One of the legs of the small right triangle corresponds to my 5.4, the side of the big right triangle. And I know side x, this leg over here, is going to correspond to the entire side of the large right triangle. Now I've got a proportion, so I'm going to go ahead and solve it and cross multiply. So I get 5.4x equals, and I'm going to distribute this 3 in, 3x plus 54. Subtract over my 3x. I get 2.4x equals 54. Divide both sides by 2.4. And I get 22.5 for x. So I know this is 22.5 for this side, and then if I add 18 to that, that's going to give me 40.5 for that whole side over there. All right, so the question says, can this cup hold more than 1 liter? Justify your answer, be careful with units. So we want to know if it can hold 1 liter. Before we can figure out if it can hold 1 liter, we want to find the volume, and in this case, our units are centimeters, so we want to know the cubic centimeters that it can hold, and then we can convert that into liters after. So you're given centimeters, so find the volume to see how much it can hold. And then we can convert it to liters and see, is it more than 1 liter or is it less than 1 liter that it can hold? How much it can hold. All right, so to do that, to find the volume of our cup, we need to take the volume of the whole cone minus the volume of your small cone. We also need to know our formula, which we said on the front was 1/3 pi r squared h. So for each of these, we're using that same formula. So I'm going to have 1/3 pi r squared h minus the volume of the small one, 1/3 pi r squared h. So now let's find what is the radius of the whole cone, of the big cone. Oops, went too far. So the radius of the big cone, so this gray cone right here, that whole thing, is 5.4. So I'm going to substitute that in for my radius. So I have 1/3 pi times 5.4 squared. And the height of my entire cone, I just found when I added, sorry for all the scrolling, added the x to 18 right here. That gave me the length of that entire height of the cone, which was 40.5. And so I'll sub that in. Next, we'll look at the small cone. So the small cone, I need the radius of that. So my small cone, so right here, the small cone, I couldn't see it, sorry. Okay, the small cone, the radius is 3, and the height right here is just 22.5. So I'm going to sub that in. So minus 1/3 pi, the radius of my small cone is 3, the height is 22.5. So that's because we found x using our similar triangles. So now it's a lot of typing this stuff into your calculator. So I type this gray part in, and that gives me 393. Again, pause your video and make sure you know how to do all this on your calculator that you get those same answers. Subtract 67.5 pi, so that would give me 326.16 pi. And let's just get an idea of how many cubic centimeters that is. So type in 326.16, which you already have in your calculator, times the pi key. And that gives us 1,024.66186 centimeters cubed. So this is how much that the cup can hold in cubic centimeters. That's our volume. But we want to know, can it hold 1 liter, more than 1 liter? So if you look at the top of your reference sheet, which I just snipped and put right here, you see here that we have 1 liter is equal to 1,000 cubic centimeters. So I'm going to convert this to a liter now, although you might be able to tell just by looking because you see that it's over 1,000. But let's convert it just to get that exact amount of liters. So convert to liters using that. So I'm going to take, and you may not need to use the picket fence method. You might just realize, oh, well, I know I just need to divide. And this is cubic centimeters. I want to get my cubic centimeters to cancel out, so I'm going to put them in the bottom and liters in the top. I know 1 liter has 1,000 cubic centimeters, so I'm just going to take my answer and divide by 1,000. And that's really just like moving my decimal over 3 places. So I would get 1.0246686 liters, which is more than 1. So the answer is yes. Yes, it can hold a little more than 1 liter. Sorry, I'm squeezing it in down here. And that answers our question. Okay, so that's what I meant with be careful using those units. So again, a frustrum or a truncated cone or a cup all mean that same thing. It's just the top part of the cone or the bottom part, depending on how you're looking at it. But you're taking off the part of the cone that is still a cone, so it has that vertex there. Okay, I hope you guys are staying healthy, loving math, doing math dances. I miss you guys. Hope to see you soon. And that is it for me. So, pi